So on page 84, I give the official definition of a Taylor polynomial for nth degree, which builds off of that relation that we developed on the previous page. All right. So, and you know, we'll get into just how to build it in a sec, but you know, it's pretty straightforward because it's really just a process where you have to, I mean, there's a little bit of grunt work that you have to do, but it is a matter of just making some substitutions and you pretty much have it. All right. So if we have an a value equal to 0, we have what's known as a Maclaurin polynomial. So the Taylor polynomial could be centered around any a value. The Maclaurin polynomial is specifically an a value of 0. All right. So if I want to have a p sub n, well, in this case, p sub n being where n is equal to 5, then what I'd have to do is really just kind of carry out the Taylor polynomial until you have an n value, you know, that n represents the level of the derivative. I would need to keep going until I got to the 5th derivative of the given function. All right, so p5 of x means that we have to go out to the 5th derivative. All right. Fortunately, the trig functions, sine, cosine, and any constant multiples of those, they oscillate back and forth between sine and cosine. All right, so f of x, sine of x, f prime of x, cosine of x, f double prime of x, negative sine of x, f triple prime, negative cosine of x, f quadruple prime, but we just say f4 of x, is going to be, so we cycle back to sine of x, and the 5th derivative is cosine of x. Now, we're looking for a Maclaurin polynomial, so we let a equal 0. So I need f of 0, f prime of 0, double prime of 0, triple prime of 0, 4th derivative at 0, 5th derivative at 0. Penmanship is kind of getting away from me here a little bit, but we do know that at 0, sine functions are all equal to 0. So the original function, the 2nd derivative, and the 4th derivative. Now, cosine has a value of 1. Negative cosine is -1, it's just negating the 1, and then back to a positive 1. All right, and so if we follow the model, it's really just building off of what you see here, and by here I mean here. Just make that a little thicker. So p sub 5 of x is going to be equal to, so f of 0 is going to be 0. So 0 plus, and I'll write it in its full glory here first, plus f prime at 0 is going to be 1 times x, plus f double prime is going to be 0 over 2 factorial, all right, times x squared. So the progression here is, and it's not shown, but it's really there. This is really assumed 0 over 0 factorial times x to the 0th power, 1 over 1 factorial times x to the 1st, 0 over 2 factorial times x to the 2nd. So once you have that that progression in mind, it gets a little bit easier to see where you're going with this. All right. So plus, the next one was -1 over 3 factorial x cubed, back to 0, and then the last one would be 1. So plus 0 over 4 factorial x to the 4th, plus 1 over 5 factorial x to the 5th. All right. So we can get rid of anything that has a numerator of 0. So x minus, so these are gone, 1 over 3 factorial, but I can say x cubed over 3 factorial, plus x to the 5th over 5 factorial. All right, x minus x cubed over 6 plus x to the 5th over 120, which is what I stated on the previous page, was a polynomial approximation for the sine function. All right, so we've already got some visual evidence that this is going to be a valid approximation. All right, so it was the statement in the problem that told us to only go out to the 5th derivative, but we could have gone out to the 50th derivative. Eventually, we're going to want to make a decision on how many terms we would need to go out to in order to get a really good approximation, but that's a different conversation for a different moment. All right. It says, what is the value of p sub 5 of 1.2? There's a couple ways to do this. One would be to go into the table and get a ballpark estimate. We're not really interested in that. What you can do instead is go to alpha. You'd hit alpha trace. It's a little different on my screen. Yeah, alpha trace is what you would do. So I'll put in y1. That's actually the original function. And type in a 1.2. So the value f of 1.2 is about, marker, 0.932. And then alpha y2 was my polynomial, 0.933, if I'm rounding to 3 significant. All right, the error is symbolized by the difference between the two as an absolute. All right, so, I mean, that's not difficult. 0.933 minus 0.932. It's about 0.001. All the absolute's telling you to do is drop any negatives because we're not interested in the direction. All right, so that's a pretty close approximation. But now what we're going to do is get a little bit further away from that center value. If you're familiar with Newton's methods, it's kind of along those lines. All right. Yeah, so 0 is what this is centered around. The a value is 0. And so the closer you are to 0, the more accurate your approximation is going to be. All right. So let's see what happens when it's 2.1. So alpha trace, I'll do the y2 first this time. 2.1. We're looking at about 0.897. Alpha trace y1, again a 2.1, 0.863, so a little bit more of a deviation. All right, so 0.897 minus 0.863, roughly 0.034. All right, so how does the error compare? Well, it's a larger value. All right, it shows more of a deviation. Deviation, the larger value. What do you think what do you think would happen if we used our polynomial estimate sine of 2.7? It's going to be even more of a deviation. right? It's even further away from the a value. Got a little extra stuff I don't need. Delete. Even more of a deviation. All right, but at a minimum, we have a way in which we can come up with a polynomial, at least over a certain interval, that would be an effective model for the trigonometric function.